Welcome again to quantum field theory. We're going to do some quantum field theory today. The kind of quantum field theory you've seen on the fronts of textbooks. We're going to take some processes, draw some diagrams, and associate these diagrams with amplitudes. We started this off last week in our study of Wick's theorem, which is a means to an end, a means to actually calculating perturbation series. So to begin with, I just want to review the objects that we've introduced so far in the course, and then we'll take it from there. So the objective in our study of perturbative quantum field theory is to calculate these objects here. These are the endpoint functions, Green functions, or Green's functions for interacting quantum fields. So for various reasons, we're going to focus on something called phi-4 theory. I won't go into those reasons really in this course, but hopefully in the next course on quantum field theory, you'll learn why that's a reasonable theory to look at. And we want to study these objects for phi-4 theory, but in the context where an interaction term given by a fourth order power of the field operator is very small. I'm not going to define small for you. It's just a parameter lambda which we take to be small. Thus, we come to consider these objects here, and we try and calculate expansions for these endpoint functions in the smallness of this interaction parameter lambda. So the Hamiltonian for our entire system, which I haven't quite got written up there, I'll write it in here. So the Hamiltonian for our entire system is comprised of the Klein-Gordon Hamiltonian, which we've already met, plus this small term, lambda on 4 factorial phi 4x. And this small term here is the interacting part hi of our system. So lambda here is small, but the operator, the norm of this operator here is infinite. So you have to, of course, interpret everything I say in this course in a largely metaphorical sense. You can make mathematical sense of this theory in 1+1 dimensions when lambda is smaller than some critical value. It turns out that you can rigorously construct the theory, but that's sufficiently far away from physical applications that we're not going to do that in this course, and it's a tremendous amount of work.
One question.
Yeah.
The interaction Hamiltonian,
Yeah. Yeah, it should be. This is a kind of boring interaction. Now it's an interesting interaction. Here it is, phi-4. So we argued a couple of lectures ago that these endpoint functions are given by these expressions here. And this is a setup which is very, very close to being useful when we do perturbation theory in the smallness of this parameter lambda here. This S hat is the S matrix, which is metaphorically defined in this way. I'll put an exclamation mark here. Because the operators are unbounded and definitely of uncertain domain here, we can't. It's very difficult to make rigorous sense of this statement here. So I'm going to adopt the physical level of rigor in this course and just pretend that this equation makes sense. And in applications, it largely will when we do calculations. But if you want this to be defined at a level of mathematical rigor, then that's a much more complicated task, which I won't address in this course. So this hi, this is the interaction term. Everything's now in the interaction picture. I said this last week. I should say it again. Where should I say it? I guess here. Everything is in the interaction picture from now on. This saves us the bother of having subscript I for interaction, subscript H for Heisenberg, subscript S for Schrödinger. Everything's going to be in the interaction picture unless I tell you otherwise. So we just have now the task of computing this quantity here. And we're going to break up this problem into two pieces, like the hard piece and the easy piece. So there's the hard piece. I'm going to try and approximate that. And here's the easy piece. Now, at the moment, we don't have any numbers for neither the hard piece nor the easy piece. To get actual numbers out of this, we're going to have to do some kind of expansion. The main difficulty lies in S and also in the phi in the interaction picture. Both of these quantities you have to expand. Sorry, let me say that again. The main difficulty lies in the S. The phi's are in the interaction picture. We don't have to expand those. So let's just sort of stand back and get an idea for what this task will involve at a high level with no details, just so you have a feeling for what's going on. So I'll give this the label, the hard bit, the label of single star, and the easy bit, the label of double star. That's it. That's the entire sort of next third of our course. It's completely elementary on a conceptual level what we're going to do. To calculate this, we're going to expand this in powers of lambda and this in powers of lambda. How hard can this be, right? So the answer is going to look something like this. You know, in what follows, we're going to encounter an incredible amount of details. It might be the most complicated Taylor series you've ever done in your life. But at the very, very superficial, high-level view of this thing we're doing is we're taking this series in lambda on the top, this series lambda in the bottom, and truncating those series somewhere. And then we have one final task, right? We haven't, I mean, that might be sufficient, actually. You might be already happy with that as an answer, because it's an expansion. But of course, we're free to expand the bottom once again, right? Because there's some stuff on the bottom, and there's a power series in lambda. Why don't we just express the final answer as a single power series in lambda? So we can work out C naught. That's pretty easy. C naught equals A naught on B naught. That's the order 1 term. But we also have to work out C1. So this is sort of first year calculus to work out these kinds of series. Let's see if we can actually do it today. So I'll put a question mark there so I can do some working on the board. So what we need to recall is that if you've got 1 on a Taylor series, you need to recall how to convert that into a Taylor series. This is the main difficulty we face in simplifying this expression here. I'm only going to do the very simplest case here. So we just need to remember that 1 on 1 plus lambda x is 1 minus lambda x plus lambda squared x and so on. I think that's correct. Yes. Yep. And so if you use that, then we can at least calculate what C1 is in this. And we're hardly going to go beyond the first order in this course. It's already going to be sort of sufficiently complicated that we will stick only to low orders. So if we apply this to our green functions, then we're going to get an expression that looks like this, right? A naught plus lambda A1 on B naught 1 plus lambda B1 on B naught plus dot 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 dot. And then we apply this formula that we have here for this Taylor series, and then we'll have our answer already. One minus lambda B naught on B1 plus dot 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 dot. And that gives us the final answer of so just to order lambda, keeping first order terms, the answer looks like this. And then expanding this out and keeping only 0th and first order terms. I think that's it to order lambda. All right, so we got A naught, lambda A1 minus lambda B naught on B1, all divided by B naught. I believe that's correct. So C naught and C1, we now have an expression for these guys. And that is Is there a mistake? What have I done?
At
Yeah, here. Ah. Thank you. Yeah, that's bad. Yeah, it was looking a bit strange. Yeah, people are now nodding, that's good. So I could have given this exercise to you in first year, right? You could have done this calculation. Let's not forget that that's what we're doing for the next couple of lectures. Our task in the next couple of lectures is to calculate 4 things. A0, A1, B0, B1. That's our task. Calculating 4 numbers in the next lecture and maybe 2 lectures. Turns out these 4 numbers are sort of sufficiently annoying to compute that it will take us quite a while. But at a superficial level, in perturbative quantum field theory, you compute 2 Taylor series, the one on the top, the one on the bottom, and then you expand the bottom series once more, and you multiply it all together to end up with a series in lambda. And that's it. That's perturbative quantum field theory at a very high level. So now you can leave, right? You don't need to stay. If you're confident that you know about Taylor series, then you can happily leave. Of course, the devil is in the details. And it's those details that we're going to do now. Yeah, another mistake?
You don't square the B1, you square
The B0. Oh, goodness me. Thank you. I don't square the B1, I should square the B0.
there's an A0 missing, I think. Yeah. This step before. And then lambda B1 or B.
There's an A0 missing.
Yeah.
Ah, gosh, so you say. There's a A0 missing, right? Goodness me. That's what happens when you do things in your head. Is it now working? Minus E. Is it good now? Yeah. Seems to be some consensus. Good. Well, it doesn't change what we have to do, which is still calculate these 4 things. Now, to do that, we just have to Taylor expand. Right? How hard can this be? So to get you ready for this task, we're going to focus on G2 x, y. This is really the simplest non-trivial Green's functions that you could focus on. So let's get started. I've just rewritten the definition again for G, specifically for G2. To get our power series in lambda, we know at least how to do one expansion here, and that's the expansion of the exponentials. So let's do that now. We're only doing things to order lambda at the moment. So we don't even need this second term. So we know this term is of order lambda, this is of lambda squared, which is already irrelevant for this discussion, and so on. So we insert these two expansions up in our formula there. So we're going to deal with this separately. Let's deal with star first. Remember, star is the numerator. And we're going to put that expansion into the numerator. And to indicate that, I'm going to put an approximate sign here because we're putting in an expansion. So the order 1 term is easy, it's just the identity. And then we get an order lambda term, which looks like this. Lambda 4 factorial d to the 4, because I can now take that limit inside, and if you write at hi, then you'll see that you get this expression, and it's a z here, to the 4. Oh yeah, I can fix this. There. So why on earth did I write out lambda 5z to the power 4 as 5z times 5z times 5z times 5z? Seems like an odd thing to do. Well, the answer is we want to deploy Wick's theorem to calculate this object here. And Wick's theorem tells us that the time-ordered product of n quantum fields in the interaction picture is equal to the normal ordered product plus all contractions. And the only way to do all contractions in a graphical way is to have all your field operators written out one by one, tediously written out one by one. So we can do the first term straight up. It's the Feynman propagator. So we've done order 1. This is fantastic, right? Because we've actually worked out the order 1 value of the green function. Because the denominator has to order 1 just the number 1. So the green function to order 1 is the Feynman propagator. So this is not a small result. This is worth celebrating that we can even calculate order 1. It doesn't get... It won't get much better than that, I'm afraid. This is the highlight of the course, that you can do order 1. To do order lambda, we're going to need Wick's theorem to even actually get any further. And so Wick's theorem tells us that this is equal to the normal ordering of the operators, all these 6 operators, Yep. There's a lot of contractions to worry about here. So now it's worth pausing so that we don't do unnecessary work and discussing what kind of contractions are going to be left over after the normal ordering process. So if you normal order any bunch of quantum fields, you put the annihilators first and then the creators to the left. So the normal ordered, this first term here, when you normal order it and then you evaluate it into the vacuum, will give you 0. That's the whole point why we do this. So at least we can say that the first term is 0. Now, in this list of hundreds of contractions that we have to deal with, I don't think it's hundreds, but it's actually a lot. Did I write out how many we need? No. But there are many, very, very many contractions that are possible. Most of them will contribute 0. So in fact, if they are not fully contracted, if every field operator, if there exist field operators that are not contracted, this will be instantly 0. So let's write that out as an observation. That's the key observation. If there are terms involving uncontracted field operators in this normal order expansion here, then when you put the vacuum either side of it, they evaluate instantly to 0. So this is pretty good news. It means that we get to throw away most of the terms inside this normal ordering here, because like most of them will involve non-contracted field operators in some sense. So the direct implication of this observation is that only fully contracted terms remain. I'll give you an example of a fully contracted term. Okay, what's an example fully contracted term? Well, here's one. That's an example fully contracted term. I'll do another one. There's another one. At about this moment, you ought to start experiencing a kind of sinking feeling, an unhappy feeling, because if you look at just these two examples here, you can see, a question?
One question. So we just can make this expansion if we have even exponents in our interaction.
We can just make this expansion if we only have even powers of phi in the interaction. No, we can do it for odd, but the first order won't contribute.
Okay, so only the first order.
Yeah, the first order term here contributes only when you've got an even number of fields inserted in the, when you've got G2 or G4, an even n, and you've got an even number there. So that's an observation I didn't quite make in the last lecture, and it's a good one that you made it now. And that is that to fully contract a bunch of field operators, you need an even number. Because if you had an odd number here, there'd be like one left over, and that would instantly evaluate to 0. But if you had G3 and you had an interaction which had 3 powers, then you'd get a first order contribution. If you had G1 and you had an interaction which involved 7 powers, and you insert 3 field operators, G1, 7 powers, that would evaluate to something at first order. So just as long as it's even at the end. Yeah, once you see this, like, oh dear, right? Because you can see where this is going to go pretty quickly. Now, this is the moment where we begin to do real physics and real maths. So all good maths and all good physics ends in linear algebra or combinatorics or both. And unless you've done some hard combinatorics or some hard linear algebra, you have not done, according to this definition, good physics or maths. This is the moment when we confront our combinatorics that we have to do to solve our problem. We have to come up with very clever ways to count and enumerate and make sure we catch every term that looks like this. And that's the combinatorics we're going to describe that captures that is called the combinatorics of Feynman diagrams. And that's what we're going to spend really a lot of time doing. We're going to solve the hard combinatorial problem of counting and evaluating every single possible fully contracted term like this. That's what Feynman diagrams are invented to help us with. Okay, so question 1. And it's amazing how sophisticated our combinatorics has become to deal with these things. It's glorious and beautiful, the combinatorics of Feynman diagrams. But at this moment, you'd be forgiven for thinking it's depressing and boring. Right, question 1, how many fully contracted terms are there? So if you've got an expansion with 6 field operators, just like gross count, how many do we have to deal with? Well, we have to pair up the first field operator with another field operator. And then we take those 2 out. And then we've got to pair up the second field operator with another field operator. We take those 2 out and so on. So it's a simple factorial thing. If you evaluate it, for us, in our 6 field operator case, there are 15. I'll leave that as an exercise. 15 possible full contractions of 6 field operators. But there's symmetries here. And whenever you have symmetries in combinatorics, that gives you the chance to get rid of overcountings, or you can spend the symmetries to count fewer things. "15 possibilities, but how many are truly different?" Start thinking through all the contractions that you can imagine writing. Try and work out how many are truly different. Should be fewer than 15, yeah? Should be some that are the same. Does anyone have any guesses how many truly different terms there are out of these 15? Is there only one? Are all 15 contractions exactly the same? Is there more than one? Can I see a vote? Who thinks there are 3 or more different contractions? Okay, I see some people raising their hands. Who thinks there's 2 or fewer? 1 person. All right, well, we'll see what turns out to be correct. Before I do that, I'm going to evaluate these contractions, actually write out what they're equal to, so that you can see what I mean by same and different. So the example contraction 1 evaluates to delta Feynman x minus y times by delta f z minus z, delta f z minus z. Try not to get too worried by the z minus z's. And example 2 evaluates to delta f x minus z, delta f y minus z, delta f z minus z. So those two contractions, these examples that I did here, evaluate to this and to this separately. All right, are there any others? Let's have a look. Well, any contraction in this list of 15 contractions will contract x with either a y or with a z. So there's two possibilities right there. If we've contracted x with y, then we have no more choices about what will appear in the further two contractions. They will be contractions between z and z. If, however, we've contracted this phi x with a phi z somewhere, then phi y must be contracted with another phi z somewhere. And then we've only got one pair of operators left over, which by definition will be this. So actually, there's only two different kinds of contractions in this list of 15 contractions. So that's quite a cheery thought, right? We go from having a lot of contractions down to really just two different ones. And all we have to really worry about now is the overcounting. So let's call a type 1 contraction. Let's work out how many type 1 contractions there are. Well, you've got to contract x against y, so it's really counting the number of ways you can contract 4 points together. We actually know the answer to that. We did that in the previous lecture. There are 3 type 1 contractions. And if there's 3 type 1s, there must be 12 type 2s. Which you can also verify just by brute force, right? 1, 2, 3, 4. And then you've got for every choice of x and z, you've got 3 choices of how to pair up y with the remaining z's. So that's how you get 12. Let's put all this information together now to actually calculate the numerator star to order lambda. I'm missing a minus sign. But otherwise, it's fine. That's pretty great. So we've actually evaluated now the numerator to order lambda. So if you're picky, you might argue that there's something a little bit wrong with what I've written here. So if you know about the Feynman propagator and you know what happens when the Feynman propagator goes to 0, you should be legitimately disturbed by an expression that has delta f of z minus z in it. It's a big, nasty, infinite number. We're going to pretend that it's a finite number at this stage. Now, this is fine. This is a completely legitimate answer to our question, what is the expansion to order lambda? But for us poor humans, it's hard to keep track of all this combinatorics without making mistakes, especially if you're writing out integrals of Feynman propagators over and over again. So we're going to introduce a pictorial representation for exactly these three terms of the Taylor series. So numerator and here's the picture. We draw a dot for each field operator and we label it by its argument, x or y. And we connect two dots every time there's a Feynman propagator between the two field operators. And that's it. And so the next picture, do I write it with the integrals or not? Not. So the next picture has a delta f squared in it and a delta f. Actually, I'll rub off that I lambda, 4 factorial, make it consistent with what I'm about to do. And we'll put a plus there, actually. This is our first Feynman diagram expansion to first order. So there's some terminology we need to introduce to tell you how to get from these integrals here to these diagrams here. Okay, in this picture you can see things which we call internal vertices. They're vertices which don't touch any external points. Externals are the ones that are associated with the field operators that appear with the arguments x and y in the green function. And I've got to tell you how to associate an integral to one of these pictures. So we have to answer the question how to evaluate a Feynman diagram. Now I hope just by looking, I'm going to keep these two boards here, just by looking backwards and forwards from these pictures and these integrals, you should already sort of guess what the rules are. Rule 1, right? Every time I draw a line, I associate a factor of the Feynman propagator with that line. So here I've got 1, 2, 3 lines. So presumably the value I associate to that diagram is Feynman propagator x minus z, Feynman propagator z minus z, and Feynman propagator z minus y, or y minus z. So for every line, you write down a Feynman propagator. Then you label each vertex with an argument, x, y, z, whatever. If the vertex is external, you do nothing. But if the vertex is internal, you've got to multiply, you've got to integrate over that argument and multiply it by I lambda on 4 factorial. So those are the Feynman rules. I've just told them out to you aloud. I'll write them down. And with these rules, you'll be able to evaluate any diagram now that you see like this. And actually, the rest of the discussion of phi-4 theory will involve arguing that you encounter diagrams of this type and only this type when you do these expansions. Okay, I'm going to write down the value of this diagram in a second. Okay, the first step of the rules are whenever you see an edge with edge labels x and y, vertex labels x and y, you associate a factor delta f x minus y. So that's the first part of the rule. And that's it. That's the value of this of a Feynman diagram. Right? For every edge, you write down a factor of delta fx minus y, and for every internal vertex, you associate an integral over the argument. And let's do the example, this quite complicated example I have up there. So the value v, the value of there's 3 internal vertices. That was a beep, wasn't it? There are 3 internal vertices here. This one, this one, and this one. Oh, 4, sorry. 4 internal vertices. And there's 4 external vertices. All right, I'm going to do the Feynman propagators first. There's quite a lot of them. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 Feynman propagators associated with this diagram. See if I get them all correct. Delta f y minus z4. Delta f x minus z4. Delta f z1 minus z4. Delta f 2 minus z4. Z2 minus z3. Where's the 11th one? 2. Oh, it's 10, not 11. So it's this big mess of Feynman propagators there. And then we've got to integrate over these 4 internal vertices. So this is minus I lambda 4 factorial to the power 4 integral dz1, dz2, dz. How am I going to do this? There, that's how I'm going to do it. So that's the value of that Feynman diagram there. It's this horrible multi-dimensional integral. So I've at least argued to you that we can take the numerator and expand it to first order in lambda and represent those three terms in terms of these things called Feynman diagrams. And that if we take these rules on faith, then they certainly work for the first three terms. That was the numerator. What about the denominator? Well, that one's actually easier. So the 0th order term is 1. We know that. And then we get a factor. Oops. So the expansion for the denominator to order lambda is represented by this Feynman diagram here, the figure of 8 loop. And how many times does this figure of 8 loop appear? Because you've got all these contractions that you have to worry about on the bottom. Answer is 3. Now we can return to the goal that we started out with, which was to calculate g2xy to order lambda. And we can now do this diagrammatically. So there's no rule that says these diagrams have to be connected. They can be disconnected. Now that's not a Feynman diagram here, it's the number 3. So let's expand this now using our rules. I hope I can do this correctly. Now remember, each diagram is just a number. It's a complicated number you get by doing integrals of Feynman propagators, but they are just numbers in the end. Okay, I'm pretty sure I did that manipulation correctly. And we're going to observe something slightly miraculous. We actually get a cancellation, so I'll draw some brackets here to make it a bit more clearer. So that's pretty interesting, right? You know, this term here exactly cancels this term here. So to order lambda, this is what we get. Very interesting. Is it a miracle that this guy cancelled exactly against this guy? Well, the answer is it's well, yeah, in some sense it's a miracle, but it's a general a sign of or a trace of a more general result. All that stuff on the bottom, all these diagrams on the denominator, will turn out to cancel against diagrams in the numerator. This is not an obvious thing. We'll prove it in the coming lecture, but it's not obvious at this stage. And we can evaluate this, right? Turn this back, you know, once you've done all your manipulations, of course, this is no good. This is not an answer because it's just a picture. We want to know the exact scattering amplitude for this process. We need numbers, and those numbers you can get by reinserting the values using these Feynman propagators. And so thus we've calculated our first legitimate Green's functions with a perturbative expansion. If you try and evaluate this term, you're going to get the number infinity, so don't try. I have to integrate over z, thank you, yeah. Yes. Yes? Yeah, the Feynman propagator is symmetric in the arguments. Good. So is all this a miracle? And does everything go yeah, it is a miracle. Or does it go completely crazy when we go to second order? Well, yeah, it certainly goes crazy at second order. And at third order, it's even crazier. I don't know what the current world record is for summing up these diagrams. By computer, by hand, I think the world record must be around 3 or 4. Maybe it's 6, I don't know. But computers can get a bit further. If you program a computer with the appropriate rules, it can expand these Green's functions out to higher orders and then sum all the terms. But even computers are defeated by, I don't know, order 30, for example. There's even worse problems. These series are only what's known as asymptotic series. They are not known to have a non-zero radius of convergence. In fact, they have a zero radius of convergence. So what do you do with a series like that? Well, it turns out asymptotic series are very good for approximating things, but only up to a certain order, and then beyond that order, they get successively worse. So you have to kind of know the sweet spot where to stop. We don't beforehand, so we just experiment and match our calculations with experiments. So what I want to do is summarize the rules for how to calculate the two-point Green function to arbitrary order. And then we'll leave it at that. There's special rules. They're called the Feynman rules. Here's the answer. If you start to expand the numerator and denominator to higher and higher orders, then think through all the steps we've taken today. Step one was to do this Taylor series of S on the top and the bottom. So we've got terms of higher and higher order in there. And each of those terms have products of field operators, of more and more field operators. And each of those terms we evaluated using Wick's theorem. And each of those terms we simplified by only keeping the fully connected terms. So this is really a sum of fully connected contractions. Fully contracted, sorry, I said the word connected. Each of these terms in this Taylor series here are sums of fully contracted time-ordered products of field operators. Lots and lots of them, right? Same on the bottom. And associated with each of those fully contracted terms here, we can draw Feynman diagrams. There's an easy way to associate to any full contraction a Feynman diagram using the rules that I just erased. And then these integrals are what come from the interaction terms. So it's not trivial, what I'm about to write down, and I'm not going to prove it in this course. That's the hardest part of the combinatorics that we are not going to prove in this course. But I hope it's plausible that you sum all the possible diagrams with two external points subject to the following rules, which are called the Feynman rules. So there's zillions and zillions and zillions of possible diagrams, but there's some rules. You can't just write down arbitrary diagrams with vertices of degree 6 or something. So rule 1 is you associate with every propagator, every line, delta f x minus y. We knew that one. For every vertex inside our picture, one of these diagrams, we associate an integral Now, be wary, what I wrote down before to evaluate one of these diagrams, I'm going to change the rules slightly. So these are the canonical rules. What I wrote down before to evaluate a diagram was just an observation. So notice there's no 4 factorial here. For each external vertex, we do not integrate. We just associate the number 1. And at the end of this diagram thing, we have to divide by a thing called a symmetry factor. Now that I haven't told you about yet. So I better tell you about this before we continue. So I'll make a pretty obvious statement. Higher and higher order terms in this Taylor series become successively more and more complicated. But many of these diagrams that we write out to represent these terms are exactly the same. We get the same diagram in multiple ways. Yeah.
Is 4 factorial times 8 or
But yeah, it's a good question. Is this 4 factorial times 8 or but the Feynman diagram? It's 4 factorial times 8.
okay.
Yeah, this starts to happen. You know, if you draw down a diagram, you wonder, is it a diagram? If I wrote calligraphic D now, is this a Feynman diagram or a calligraphic D? So in these expansions, each diagram, I mean, there's only certain ways of graphically drawing a Feynman diagram. But they can occur in many different ways, and that redundancy is called the symmetry factor. And what we do when we do an actual Feynman diagram expansion is we just draw down the distinct diagrams and then divide by their symmetry factors, rather than what we did before, which was to keep track of exactly how many copies we had. This is not something that will really concern us in this course. We're never going to encounter processes where that symmetry factor is very difficult. It's a non-trivial task to determine the symmetry factor. Right, well, I think that is a good moment to stop because I've managed to introduce the Feynman rules for phi-4 theory. I should say that this is the Feynman rules for phi-4 theory. There is a different set of rules for phi-3 theory and phi-6 theory and phi-7 theory. Every theory has a different set of rules. But we've now met the Feynman rules, and our task for the rest of this course will be to make sense of these expansions and to try and extract observable information from them. But for the moment, I think it's a good moment to stop. So thank you very much.